Alright, so today we are looking at section 5.3, which gives us some more special segments or lines that we can draw into a triangle, and some additional points of concurrency that go along with those, which, if you remember, point of concurrency is the point where three or more lines intersect at the same spot. So a median of a triangle is going to be a segment whose endpoints are a vertex of the triangle and the midpoint of the opposite side. So it's going to start at a vertex and go to the midpoint of the side directly opposite it in the triangle. Centroid of the triangle is going to be the point of concurrency of the three medians of the triangle, and the centroid will always be inside the triangle. So, and then we've got theorem 5.7, the concurrency of medians of a triangle. Which tells us the medians of a triangle intersect at a point that is 2/3 of the distance from each vertex to the midpoint of the opposite side. So if I've got a triangle here and I've got all of the medians drawn in, then the centroid, this point of intersection for all of those medians, if I go from B to P, that's going to be 2/3 of the distance from B to F. So for this whole segment BF, BP is 2/3 of it, which would mean that PF is 1/3. And same thing for CE. From C, the vertex, to the centroid is 2/3 of that total length. P to E would be 1/3 of it. And A to P would be the 2/3 of the distance. And P to D would be 1/3 of the distance of AD. So this example says C is the centroid of triangle GHJ, and CM is equal to 8. Find HM and CH. So we know that from C to M, it's a distance of 8. And we also know that the length of CM is going to be equal to 1/3 of the length of HM, right? So from the vertex to the centroid is 2/3 of the distance. Centroid to the side is 1/3, so CM is from the centroid to the side. So that's 1/3 of the total length. And they told us what CM is, right? 8 is equal to 1/3 of HM. So get rid of the fraction. We're going to multiply by its reciprocal. 3/1, or just 3. So 3 times 8 is going to be 24. Is equal to the length of HM. So that's our HM length. And CH, we know, is going to be 2/3 of the total length of HM. So since we know what HM is, 2/3 of 24. So CH is going to equal 16. Of course, also, if we know that CM is 8 and HM is 24, then if you just subtract the 8 from 24, that would give you 16 as well. All right, so the next example, a little bit more complicated. I want to find the coordinates of the centroid P of triangle DEF. All right, so got triangle DEF here. Got all the coordinates for all the vertices. And HF and DG are going to be medians, since it tells us that P is the centroid. So we know those are medians if P is the centroid. And we're trying to figure out what the coordinates of this P point is. Which we can see that it's in between these two units here, between 4 and 5. But we don't want to guess at that. We need to actually figure that out mathematically. Okay, so first thing we're going to do is we are going to figure out the coordinates of point G here, which shouldn't be too hard to figure out because it's right there where we can see the intersection. So it's at the point 6, 3. Of course, had that not been at a perfect intersection there, since this is a median, then we would have known that point G had to be the midpoint of EF, right? So if it wasn't right here on an intersection, if it was kind of in the middle in between two units, we didn't know what the exact fraction was, we could have used the midpoint formula. X1 plus X2 divided by 2. Y1 plus Y2 divided by 2. So for G, we're calculating it up. It's going to be 8 plus 4 divided by 2, and 5 plus 1 divided by 2. 12 over 2, 6 over 2, or 6, 3, just like we read it off the graph. Right? So if you can't read right off the graph exactly what the point is, then you use the midpoint formula to find that point, because we know it's got to be a midpoint if that's a median and that's a centroid. All right, so then we need to figure out what the length of DG is. So, which is fairly simple because it's on a horizontal line. So the length of DG will be 6 minus 2. Just subtracting the x values. So that's a total length of 4. And then this portion from D to P, what do we know about it? Because it's from the vertex to the centroid. We know that it's got to be 2/3 of the total length of DG. So DP is going to equal 2/3 of DG, or that's 2/3 of 4, which 4 times 2 is going to give us 8/3. So we know the length from D to P is 8/3. To get the x coordinate for P, though, we're starting at D, which is at the 2 on the x, right? So to find P, or the x value for P, that's going to be 8/3 plus 2, figuring out that distance right there. That's 8/3 plus 2 over 1. Or if we make that into thirds, it's going to be 8/3 plus 6/3. It'll be 14/3. So, and that's the x coordinate, right? Of course, it's on the y at 3. So the coordinates of the centroid point P, it's going to be 14/3 on the x, 3 on the y. Questions there, anybody? So basically what we did, we found the length of DG, then figured out what the length of DP was. And then once we had that length, we added it to the x coordinate for D to get the x coordinate for P. And then we just used the y coordinates, 3, which, since that was on a horizontal line. All right. So moving on then. Another segment that we can draw into a triangle is the altitude of a triangle, which is going to be the perpendicular segment from a vertex to the opposite side or to the line that contains the opposite side. An altitude can lie inside, on, or outside the triangle. So depending on what kind of triangle you have, you can draw. The altitude may fit perfectly inside. It may be on a side of the triangle or outside the triangle, which here would be an example where it would be on the outside. Right? So if you've got an obtuse triangle here, to go from point A across to the opposite side and hit it at a right angle, you actually have to extend this base side down here out so that you can draw a line that's going to go straight down and hit that line at a perpendicular or at a right angle. Right, so that's why it says from the vertex to the opposite side or to the line containing the opposite side, because you may have to extend the line out for that opposite side so that you can draw the altitude in. And then the orthocenter is going to be the point of intersection of the concurrent lines containing the altitudes. So centroid is for the medians, where they intersect. Orthocenter is where the altitudes are going to meet. And then the concurrency of altitudes of a triangle theorem says the lines containing the altitudes of a triangle are concurrent. If AE, BF, and CD are altitudes of triangle ABC, then the lines AE, BF, and CD intersect at some point H. Right, so all of your altitudes are just going to be concurrent. There's no mathematical formula or anything that goes with it. So that theorem just tells us that they're all going to intersect at one point. So here we want to figure out where is the orthocenter located in triangle ABC. So the first one said if the measure of angle A equals the measure of angle B equals the measure of angle C. So if all three angles have the same measure, then that would have to be an equilateral, equiangular triangle. So triangle looks something like this. And then, so if we're looking for the orthocenter, that's going to be where the altitudes meet. So you got to go from C straight across to AB so that it intersects at a right angle. From A over to CB, where it's going to intersect at a right angle. And technically, to find the orthocenter, or actually any of these points of concurrency, it really only takes two lines if you draw them in properly, because where those two lines intersect is where the third line should go through, right? So there's two lines there. My third line, when I draw it in, should look like it's perpendicular to the other side. All right, so that ortho center is inside the triangle. Kind of almost in the exact center of that triangle. All right, so then the next one says B, if the measure of angle A equals the measure of angle B equals 45 degrees. So if A and B are 45-degree angles, then what's the measure of angle C? It's going to be a 90-degree angle, right? Because 45 plus 45 is 90. Subtract that from 180, that leaves you 90 for the third angle. So if that is a right angle, then if I draw in an altitude from A to the side opposite it, to side CB, then technically I'm just going straight down this side, right? Because it's going to intersect at a right angle, at the right angle for that triangle. Same thing for going from B to side AC. It's just going to travel straight down that side because that side does intersect at a right angle with the other side. And then your third side, something like that. So our ortho center is right there at point C, where the right angle is in the right triangle, which should be the case for any right triangle that you have. The centroid, or the ortho center, should be right there at that intersection of the right angle. So we call this on the triangle. And then for this triangle ABC, it's an, what kind of triangle? It's an obtuse triangle, right? Angle BAC is an obtuse angle. So now to draw this in, you go from point B up here to side AC. I can't come over here to anywhere in AC because that's not going to make a right angle. So this is one of those situations where I have to extend out the side, which then will allow me to draw a line that goes from the vertex straight down and hits that segment at a right angle. And then the same thing for drawing in from C to side BA. That's not, this isn't a right angle here. So to make a right angle, I've actually got to come out here somewhere. So I'm going to have to also extend side BA. And then from point, let's see if I can draw that straighter. Looks a little better. And then from that point through point a look something like that. So our intersection point, our ortho center, is way out here outside the triangle. All right, and that's the notes for section 5.3.